So this lesson is all about taking nonlinear data and making it linear. Okay. And we do that essentially by taking our X, our Y, or both sets of coordinates and taking the log of each one. So now there's a nice ways to do regression by your calculator. This is a little bit of an old method, but it has a lot of actual uses still. Okay. You used to have to linearize all yours because the regression equations only worked for linear. So, representing data with a wide range on a graph is always challenging. If the data rate of change is compared to absolute values, representing the whole data on a single graph can often be achieved by changing the scale on one or both axes. So sometimes what happens is you get all your data, most of your data clustered into a little part, and then you've got other stuff spaced out way bigger. And the area where most of our data is all crunched together, so it seems not important. Logarithms are one way to do that. Solving equations can somewhat seem formulaic and void of creativity. Theory of knowledge connection. Does math lack creativity? Not really. There's a lot of creativity needed to solve real problems using math. And so it sometimes can start lacking creativity. You got to learn how to do it this way, but it opens up and uses all kinds of things. And yes, the creativity is often positively correlated with the expansion of knowledge. So, how and when to do this? Anytime it tells you is when. So here we've got an object and its approximate size in meters. From the proton to the atom to the blood cell, diameter of human hair, a human, I guess that's height, a giraffe, a blue whale, the moon, the earth, the sun, the solar system, the Milky Way. If we tried to put all of these together, notice how if I take the natural log of all of these, they always start to become like reasonable size numbers. These ones don't become essentially grouped on top of each other. And sure, there's plenty of things in between these, but
See any of the small ones?
you would not see very many. The small ones are all going to be this atom, all clustered in that one thing. Protons, neutrons, electrons are going to be clustered around here. Hair, different bacteria all kind of clustered in there. And you get a lot clustered in here. And we don't have a lot of things between the size of normal things on Earth and the moon. I don't think a blue whale's actually 30 meters long.
Huge.
Like 95, 100 feet?
No, they're huge. Maybe not 30 meters.
I,
I wouldn't be surprised if they were 25.
I was thinking they were more like 30 to 40 feet. They're bigger than
I
that?
think they're bigger than this. We can look it up.
But does that make sense how the logging the axes can scale that?
30 feet's like really big for one.
30 meters? That's nearly 100 feet. Um, so we can take this, if you look at this graph here, this is the planet's distance from their sun. Again, here we've got it starts to get real big real fast.
Science, we like graphed this out like on a lawn.
Uh-huh.
In the yard, and it was like crazy because it's like.
Yeah. And so, we've got 57 million, 149 million. These are all, kind of, and then you got this huge jump to 778. Then you're at basically almost doubling it to Saturn, from Jupiter to Saturn. Then nearly doubling it again from Saturn to Uranus, which is basically all six of these Mercury to Jupiter or Mercury to Saturn would fit in between Saturn and Uranus. And then almost again, Uranus to Neptune. Neptune to Pluto is actually not all that far.
So
It's a dwarf planet. It's not big enough to be a planet. Yeah, not quite, because it cuts inside of Neptune at some point. So, if they did it with log base 10 this time instead of log base E, and all of a sudden these kind of fit much, much simpler. They all fit between 7 and 10. So, linearizing. Here's how we do it. A table gives us the growth of the number of bacteria cells here. And if we graph them, we get something that looks like this, which looks kind of terrible, doesn't it? But maybe kind of sort of exponential. But it kind of makes a very, very bad curve. So
it almost looks like a logistic sheet, but not flat.
maybe
Good curve.
it doesn't make any good curve.
You might want.
Maybe, but we're making that judgment based exclusively on this one point at the end, which is a dangerous thing to do. So what we're going to do is we're going to take this, we're going to throw it into our graphing calculator, and we'll try a few things. See what gets kind of linear. So
So wait, linearization is just trying to
make it linear by altering your axes. So how to do this? We're going to take it in, stick it in. The bacteria is going to be back. We do tend to know that bacteria tends to grow exponentially.
I forgot that this was bacteria. Oh, yeah, it's
Because we just got into the doing math and then forgot what we were actually talking about. Now, towards the end, bacteria does level off, so maybe it is logistic. What I'm going to do here is I'm going to take the log of both axes.
Yes.
I don't really have to hit the equals, it would just show up.
You're getting this. How did you get this?
Okay. That's not helpful when the first one is undefined. So in this formula column, I just put it in. Now, I know that logging with exponentials, logging the y-axis tends to linearize it. But I'm going to add a page and I'm going to add data and statistics. So first thing we'll look at is time. If I put bacteria here, I get the crazy graph they had. Let's see what ln(b) is. That's kind of linear. Is this going to work with ln(t)? Yeah, it's just going to kind of ignore it. That's actually probably worse.
I think it's better.
Okay.
Well, oh,
Oh, wait.
no, because we switched to actual lines. It's like a.
Tangent.
Yeah, there we go.
So establish this.
This is kind of the best one.
Tangent is equal to sum of.
So what we're going to do here is we'll make the regression. We'll show linear. I like ax plus b better when I'm linearizing. So if it's nonlinear. Because ultimately,
What's the difference between AX plus B and X?
it's a plus bx.
Oh, okay. I was like, what?
A plus bx, sorry. So ultimately I have, let's switch the color, like this color. ln of b, because that's my y-axis, right? Equals 3.76 plus 0.241 t. And that's actually my equation. Now I want it to be b equals. How do I undo an ln?
Put it to the E, like base E.
I could have done this with a base 10 log too, and then I'd use base 10. Okay, so this becomes b. And that becomes that whole thing. But we can simplify this. Because laws of exponents say that these are equal. E to the 3.76 is just a number. In fact, it's 42.9. There we have it. A nice exponential model. Oh, they did something else too. What they did, which I'm not sure why they did this, but they essentially did this using exponent rules again.
Off.
So when you have these, you multiply the exponents, and then they did e to the 0.241 is 1.27. So they took this answer, which is perfectly legitimate, unless they say show, and say you have to get it to this. So this, I guess that they did x instead of t, but this when I multiply the exponents in this parentheses, so I can reverse it and pull the t out. And then I can just take the calculator and do e to the 0.241. And that's 1.27.
Oh, wait, I'm just looking at the calculator. This number. Okay.
So now we're gonna do a new one. And this is weeks, and I think it's gross movie profit. There's a lot of data here. So it's going to be important to look that I don't have something that feels way off because they're very big numbers. And this is what happens sometimes when you get very real data. It takes a while to enter it.
Sam, I need to like write down like my table that I've entered into the spreadsheet.
No, not if they gave it to you. They would give it to you, so you don't need to rewrite it.
That's with the axis though.
You don't need to write, you need to show that you did that. Or with a graph maybe that says LNY or LN week or something like that. So first thing I'm going to do is actually check that I entered these correctly. Week versus gross. Okay, I've got nothing that looks like it doesn't fit the pattern. This looks like a logarithmic graph, so my guess is I want to log the week. And I'm just gonna, they chose ln on this one.
So if it's exponential, then
Log the y. If it's logarithmic, you'll log the x. If it's powers, you'll actually log both. And we'll get to that. They call this semi-log because I'm logging one of them. What I often do is I'll just log both of them and check what looks the best, like I did on the last one. And it's lovely to just let my calculator generate this for me. And this gets kind of linear. It's not a great fit, but it's a fit. Um, so I can menu analyze regressions. I'll show linear like that again.
logarithmic, then it would perfectly linearize, right?
Mhm. Um,
So this just tells us that it wasn't a perfect.
it was not perfectly logarithmic. Remember that if I do it from this calculator screen, stat calculations, um, LNW was there. I can get an R and an R squared. Oh, it says it fits pretty well. It says it fits to the line. I guess it's pretty tight to the line. Although I do start to see a pattern here at the end.
If it continued on further in the same pattern, it wouldn't be very
It
good.
would go veer off the line.
Oh,
So that's where potentially extrapolating or things becomes dangerous. So we get this kind of crazy graph. Okay, let's clear you out. So I'm getting gross equals 2.13 times 10 to the eighth. Okay. And did they want to do anything like that? Or did they? Well, I guess we want it to be a logarithmic equation, so they wrote it out with actual numbers. 1861240 ln w plus 213186757. And we want it to be a logarithmic curve, so we just have to leave the ln.
yeah.
So example 3 is your quick quiz questions. Semi-log means we're logging one of the axes. What would semi-log be used for? What type of models?
Exponential.
Exponential and logarithmic. Log is going to be used for powers. So here's our distance from the sun. We're going to answer a whole bunch of these. Distance and orbital period in days. So
I'll just log both because both the X and the Y are like crazy.
a little bit crazy, yes.
Yeah. Oh, this makes sense.
So now we're going to do a new one on the calculator. $57.92. So this is in millions of meters, the distances. And this is actually done partially in the pre-calc book. They do not have Neptune or Pluto, or they don't have Uranus, Neptune, or Pluto on it.
Mine was I think not. This is the one we. Hold on. We're looking at my great grandpa statue in this track. That's you.
So I'm just going to ln both axes. I know I'm going to have to. So now when I add my page, and I'm just, so if I did distance versus period, I get very crowded together at the beginning, right? So we're going to change both of them. And we get really linear. Uh-huh. So ultimately, I need to think of this as ln(p) equals negative 1.61 plus 1.50 ln d. I will raise both sides to the power of e, giving me just p on this side. E to the negative 1.61 plus e to the 1.50 ln d. And I can do a couple of things here. Get e to the negative 1.61. This, I cannot just cancel the e and the ln until I bring the 1.50 up there. With my calculator, I'm going to do e to the negative 1.61. Wait. That's 0.200 when I round it correctly. Those cancel, or d to the 3/2. Period is 0.2. This will change depending on what we measure distances and periods in, but d to the 1.5 will stay the same. And that is one of Kepler's laws. Does that kind of make sense for linearizing? A lot of times I just take the ln of both. If I'm not sure, is this exponential or is this power? I'll do the ln of both and see what comes out better. And sometimes I will take the calculator, see what has a better r squared. Or sometimes I go, this makes more sense based on what it mean, the meaning of the question to be exponential or powers.